So our next speaker is Jason Zhao, who will talk about determining optimal test functions for the two-level densities of L functions.
All right, thank you for the introduction. Before I begin, I'd like to mention that this work was done in collaboration with Ella Boliru, Fangu Chen, Charlie Devlin, and I was advised by Stephen J. Miller. So Stephen always tells me to always begin my talks with something profound. So I'd like to start with, I guess, a very interesting connection between random matrix theory and analytic number theory, namely the Katz-Sarnak density conjecture. So Katz and Sarnak noticed that if you study the distribution of normalized eigenvalues for a random matrix ensemble, then these distributions seem to model the behavior of zeros of L functions associated with cuspidal new forms. So just to go through some notation and some terminology, we have an L function LSF, where F is the cuspidal new form, and CF is the analytic conductor corresponding to this L function. And just so that everything's a little bit more interesting, we assume the Riemann hypothesis. It's not terribly important for the talk, but just keep that in the back of your mind. And I'm deviating a little bit from the convention. So when I say test function, I mean a non-negative even Schwartz class function, which has compactly supported Fourier transform and is non-vanishing at the central point. And so from here, we can define the one-level density, which is just essentially just a weighted sum of the zeros. And we have this normalization factor of log CF over 2 pi. This is just so that the low-lying zeros of the L function all have mean spacing 1. And essentially, this measures the density of the zeros near the central point. So in practice, it's impossible to calculate what the one-level density is. So instead, as good analysts, what we do is compute averages over finite subfamilies of cuspidal new forms. And we do that by indexing over the analytic conductor. And then we take this average. And if our family is sufficiently nice, as we take Q to infinity, actually what pops out is this integral of the test function against a distribution. Now, in line with the Katz-Sarnak philosophy, the distribution is conjectured to be dependent on a symmetry group G, which ends up being one of the classical compact groups. So again, in line with the philosophy, we use the notation instead of WF, we use the notation W1G to denote one-level density and also the symmetry group. And here are just some examples of what some of the distributions end up looking like. The n level is very, very similar, but instead we sum over tuples of zeros. And again, if our family is sufficiently nice, we get this nice convergence as Q goes to infinity. Though again, as all things, if we work in generality, the distributions end up looking a little bit more intimidating. So what exactly is the problem and what exactly is the motivation for the problem? So what we're interested in is the average order of vanishing at the central point. And as it turns out, these n-level densities, they are perfect for actually giving us estimates on what this average order of vanishing is. As you can see, these integrals, which end up popping out from the convergence, they end up bounding these limits on the average order of vanishing. And the goal is to minimize the right-hand side of these inequalities. So for the one level, the idea is essentially just to use some functional analysis to reduce the problem to a differential equations problem. And you can find the bulk of this work in Onelevel and Sarnak, and also the work of Freeman and Miller. As for the two-level densities, things get a little bit more complicated because you're working with one more dimension. So instead, what we do is look at a restricted problem where we only consider test functions which are products of single variable test functions, phi1 and phi2. And then to go even further, we fix one of the test functions, in this case, phi1. And this essentially just reduces the two-level density problem to one analogous to the one-level density problem. So just to get some perspective on what exactly the numbers look like, we have our test function, phi1, which is this thing right here. And just to get some idea on what exactly the bounds look like, we can obtain some naive estimates by choosing our test function to just be the product of phi1 plus itself. And so as you can see, the naive estimates, they're pretty good, but the optimal estimates, they give considerable improvements, where the optimal estimates are when we find the optimal phi2 for phi1. And then some applications to the order of vanishing. Again, as you noticed in the previous slide, we have the weighted average order of vanishing. So we have this weighted sum over here, which is bounded by this interval over here. And of course, why we're interested in the higher levels is because they give better estimates for higher orders of vanishing. So here, because we have this weighted sum over here, we have this weight 2 over here bounded by this, and dually we can get some nice lower bounds on lower orders of vanishing, namely 0 and 1. So some key observations. How do we go about finding these optimal test functions for, say, the one-level densities? Well, the first observation is by Aheiser's theorem and the Cayley-Wiener theorem. We have this very, very nice correspondence between test functions in L2. Namely, if we have a test function which is supported where the Fourier transform is supported between -2 sigma to 2 sigma, then there exists a L2 function which where the Fourier transform is just the convolution of G with its check. Now, the second observation is a favorite of harmonic analysts, is that by the Poncharel theorem, we can look dually towards the Fourier transform side. So why is this particularly useful? Well, again, remember the Fourier transform of these test functions are compactly supported. So we're moving from a integration over the entire real line to one over just an interval. Moreover, the Fourier transforms of our distributions are very, very nice. So instead of working with like sine x over x, we instead have this very, very nice delta function plus some very simple kernel function m, which is just a real valued even step function. So the first step for the one-level density is to just convert to a minimization over L2. This is just so that we have more access to functional analytic tools. So we define the self-adjoint linear operator K, do some expansions, do some algebraic manipulations, and then out pops this very, very nice equivalent optimization problem over L2. We have this functional R, and then subject to some linear constraint where G is not orthogonal to 1. This is just so that the denominator is not non-zero. And then we use some functional analysis. So I won't belabor the details, but we have this degenerate case where -1 is an eigenvalue. In this case, we have that the R achieves the minimum 0. Obviously, in our scenario, we don't really have this degenerate case. More interestingly, if -1 is not an eigenvalue, then by the Fredholm alternative, there is this unique F0, which gets mapped by I plus k to 1. And moreover, the 1 over the mass of F0 is going to be exactly the minimum of R. And F0 is also the minimizer of R. And again, remember, we have this correspondence between L2 and test functions. So in fact, the optimal test function is going to be just, the optimal phi is just going to be F0 convolved with itself, or I guess convolved with its check. But usually F0 is going to be real and even. So challenges for moving to higher levels of density. So first of all, why are we actually interested in higher level densities and also larger support? Well, larger support, that's kind of obvious, where if you're optimizing over test functions with larger support, we have a larger space, so we get better upper bounds. Why are we interested in higher level densities? As I mentioned a bit earlier, we have bounds on the weighted average order of vanishing. So this gives better estimates on higher average orders of vanishing. Now, unfortunately, there are two main obstructions to this. One, for small support, these do not detect non-constant kernels. So for example, in the symplectic group case, we have this kernel here, which is just 1/2 of the characteristic function of -1 to 1. So if we're looking at test functions which are supported between, say, 1/2 or -1/2 to 1/2, then the kernel is just constant. So we don't get anything too terribly interesting out of that. But instead, if we're looking at test functions which are supported, say, between -2 and 2, then there's some complications and there's some additional computations that have to go down. The second main obstruction here is that for As you saw earlier, with the higher level densities, the distributions, we have these very, very nasty determinants, and they're much more complicated to work with. And moreover, higher dimensional integral operators, they're not as well understood as single variable integral operators. So as I mentioned earlier, to resolve these or to kind of bypass some of these challenges, we do some simplifications. So first we fix a test function phi1 with support with the Fourier transform supported between -1 and 1. And then we want to minimize this particular quantity here over test functions phi2 with Fourier transform supported between -1 and 1. So just to work through an example, we have this Fourier pair of the distribution. And for phi1 arbitrary, if you work through the details, if you run the numbers through, out pops this delta function and this even kernel here. So again, very, very similar to the one level density case. And then, though obviously we have this constant factor which we have to normalize for, which we do. So we have V is just delta plus the Dirac delta mass plus some even kernel, where this M is just M tilde normalized by C. And then we just rehash everything in terms of the one level density, right? A very, very similar scenario where we're minimizing this quantity over here, where V is just delta plus some kernel. And now we can just collect the one level goodies. So as you might recall, as I mentioned earlier, by the Fredholm alternative, there exists a unique G in L2 satisfying this integral equation here, which was just I plus K mapping G to 1. But of course, you can rephrase it in terms of an integral equation. Moreover, accounting for the normalization, the 1 over the mass of G is going to be exactly the minimum of the quantity that we want. So to go back a bit, why did I choose the Fourier? Why did I choose phi1 to be this thing here? Well, as it turns out, for the one level densities, if you're looking at test functions supported between -1 and 1, the optimal test functions all end up being scalar multiples of phi1. And obviously, for this optimization problem, everything is kind of scalar invariant. So we just consider phi1 to just be sine 2 pi x over 2 pi x, all quantity squared. And moreover, the Fourier transform is very, very nice in that it's just a linear polynomial in absolute value of x on between -1 and 1. Moreover, the kernels from the previous slide, or the previous two slides, all take the form, where the kernel M, that is, these all take the form of quadratic polynomials in absolute value of x on the interval -1 to 1. So if you remember your single variable calculus, if you differentiate your polynomials enough times, everything just vanishes. So what do? You differentiate under the integral sign. So this is a very nice, cute little exercise where you just differentiate the quadratic kernel, and then out pops out from your, so again, we're going back to the unitary example. So out pops from your integral equation two very, very nice differential equations. So this last one, as some of you might recognize, is just the solutions are exactly just trigonometric polynomials with period 2. And so if we assume evenness, we can just throw out the sign terms and then do some back substitution in order to get to recover the closed form gx is equal to a cosine 2x plus c, where a and c you can just obtain from back substitution. And this is just what some of these optimal g's look like. So how do we go even further? So we have these optimal g's, and then recall that the optimal test functions are just g convolved with themselves. The g functions convolved with themselves. Obviously, everything's even and real, so we don't have to deal with any of the check stuff. But so we have this optimal phi2. So the question becomes, okay, we have this optimal phi2. What is the optimal, say, phi3? And so we don't really have access to the same tools as we did before, because we have all these cosine and sine terms. So before we had these trigonometric quadratic polynomials, but now we have trigonometric polynomials coming up in our kernel. So we can't really use the same differential equations trick. So what we do now is, again, we define this operator K, where we have the kernel M, where M is now dependent on phi2. And this, as it turns out, that for the unitary group, this is going to be a contraction mapping. So this series over here converges absolutely and also uniformly on the interval -1/2 to 1/2. And in fact, it's the unique continuous solution to the Fredholm interval equation here. I plus k, G gets mapped by I plus k to 1. So summing, and as it turns out, all these terms over here, when you integrate, when you iterate kn of 1 and you integrate, all these terms for the unitary group are going to be positive. So summing actually does give a good upper bound. And so we sum 5 terms in order to get this new bound of 0.488. And if you compare to the original table over here, we have a point on the order of, say, on the 100th place of improvement. And so again, the question becomes, how far can we push this? Can we do this? I've only done this for the unitary group, but for the other groups, it's a little bit more complicated because, again, you're doing these iterates. So this method is a little bit suboptimal in that you're dealing with n many integrations. So it's a very, very slow process. And also, I conjecture that for the other groups, these terms over here, you can integrate kn of 1. That for all the compact groups, it's going to be positive. But again, it's hasn't been proven yet. But it seems to be the case for the unitary group, or it is the case for the unitary group, and it seems to be the case for the first, say, 2 or 3 terms of the other classical compact groups. But again, the question becomes, like, is this worth pursuing? I don't know, right? Because this is very, very computationally intensive. You know, when I ran this in Mathematica, it took like what, 4 hours in order to do 5 terms. You know, I kind of shuddered to think how much 10 terms does, or how long 10 terms will do. But yeah, and again, for references, if you want to look more into the one-level density stuff, I recommend looking at Freeman and Miller, and also Awani, Liu, and Sarnak.